Hello everybody, I'm Albert López and today we will be talking about the minimum positive influence dominating set problem, which is a combinatorial optimization problem with interest in social sciences. First off, we will start talking about the problem itself and why it's interesting. Then we will move on to the proposed algorithm, and finally we will do some experimental evaluation on why our algorithm is the new state-of-the-art method heuristic for solving it. So first off, we need to define what is a positive influence dominating set. It is a dominating set which also verifies that at least half of the neighbors of each vertex of a given graph are inside this set. This means that, unlike the dominating set problem, we don't count as covered a vertex which is in the subset of the solution. We will still need that at least half of its neighbors are inside the solution also. And this makes it interesting because it's kind of complicated to solve it computationally. And the main interest of this problem is in social sciences such as psychology and marketing. And it was first posed as a trial to improve the efficiency of anti-tobacconist campaigns, anti-alcoholism campaigns in teenagers, and so on. And let's move with an example. Here we have a connected small graph, and we propose a solution, which are the dots in red. As you can see, all the vertices with only one neighbor are covered by this neighbor, and the others also verify the property. If we take a closer look at, for instance, the neighbors of C, we have that the neighbors of C are A, E, and G, and as A and G are part of the proposed solution, C is covered, and this also applies for any other of the vertices of this graph. So our main objective is to find a set of minimum cardinalities such that it is a positive influence dominating set for a graph. And the main problem on doing this is the following, and it is that this is a NP-hard problem, which was proved some years ago, and it gives a rise to the question that can we solve it efficiently with approximated methods? That is, maybe we don't find the exact minimum set of cardinality that verifies this property, but maybe we can find a set with set small enough that verifies this property and that satisfies for most the requirements of the applications of these problems, such as its origin, which is campaigns for public health, or maybe marketing campaigns, and so on. And let's move on to the proposed algorithm. Our algorithm is a modification of the ant colony optimization, which at its turn is an algorithm inspired by the attitude of ants foraging for food. And what they do is they leave pheromones on the trails they use to collect food. And over the time, the accumulation of these pheromones alongside its evaporation, so we can deny some very low interesting trails, and it allows us to, from a very complex network of possible trails, find the best one to a given source of food. This was proposed by Marco Dorigo, and we will use its framework, a later framework he developed, the Hypercube framework, to apply this algorithm. And the main way of proceeding with this is we have a combinatorial optimization problem, and then we can consider all the possible solutions of it and decompose on solution components. And having in mind the solution components, which are the essential blocks that build any solution, and for the most, it can be any kind of solution components as long as we can model it like combinatorial optimization problems. There are versions of ACO, continuous, or of other kinds, but we will use this concrete type. And once we have all the solution components, which is the space on which we will move, we need a greedy algorithm, not necessarily exact algorithm, but a deterministic algorithm to build solutions, to build apt solutions. We don't need them to be minimum, but we don't. We want them to be at least good enough for proceeding with the next steps. And we have a pheromone model, which is literally a vector, which there is one number for each solution component. And first we assign all of them the same number, a base number. And then as long as we move on this circle on the right of generating solutions, taking in care the algorithm method, and also some randomness provided by the probabilities which arise from considering the quality of solutions given by pheromone, the pheromone model, we enter in a cycle in which we generate solutions, take in consideration the quality, and then we improve the pheromone model. And in the long run, some kinds of problems can be proved to converge under this kind of solution. And we will take a look at a closer friend, which is the negative ant colony optimization. It's an extension of the previous one and takes its motivation from the comportment of different insects in nature, such as the pharaoh ants, which do it for foraging food in the same way that the original ant colony optimization was considered, or Lasius niger's colonies, which use this kind of negative feedback on food sources to avoid crowding and using them all, or honeybees, which Mark recently visited flowers in order to avoid them. And this way they can be more efficient on foraging food and pollen for their hives. And what is this translated to meta-heuristic? Well, we have the same baseline idea, but once we have generated solutions probabilistically, we use an exact method of giving the best solution given a set of solution components, because we have a much smaller amount of solution components out of, let's say, 10 or maybe 100 different solutions generated randomly, but with the inspiration of the breathing method and also the pheromone values. And with this, we take in consideration the solutions which are in the best solution among those set and the exactly constructed. And we mark the good solutions in this subset of solutions and the bad ones. In reality, the pheromones don't belong to the solutions, but belong to the solution components, because we have the main consideration that good solution components build good solutions, and that's what we move on. And we will prove that at least for this problem, this works. And at the end, it converges, and if it converges too fast, we restart the algorithm and do so until some termination condition is met. So let's have a look at how we construct solutions. Well, once we have a graph we want to solve, to say in some way, we preprocess it, and by processing it, we take in consideration all the vertices that should be in any solution. Having done so, we then consider how much vertices we need to add in the neighborhood of each vertex to cover it. And once we have that, we start moving on from the lowest connected to the highest connected, as the recent literature on greedy algorithms for this problem proves that it's more efficient. And then once we have focused on a single node, we take a look at its neighbors and we add them with the following probability, which is here at the end of the diapositive. And the probability is given by first the number of the candidate vertex neighbors which are uncovered, which is the eta sub k, and then we take a look at the pheromones. The positive pheromone of this vertex provides a higher chance to be included, and the negative pheromone does exactly the opposite. This negative pheromone is built upon bad solutions, and it sees only an improvement if there's if a vertex participates in a set of solution components we observe built by the sum of different randomly generated solutions. And with this, we have a pretty intuitive way of building solutions or adding nodes. So let's move on. How we do the exact thing? Well, for this problem, we can describe it as an integral linear programming problem. And we then use Cplex, which is a library of mathematical optimization, to solve it exactly. Once we've done that, we need to consider how we update pheromones. For the positive pheromones, we update them on the classical way, on the hypercube framework for the ant colony optimization, which was also described by Mike Rodrigo, the discoverer of the method of ant colony optimization. And what we do, we have three constants which we need to determine, which are the case, and then we have these deltas. This first one is one if a given vertex v sub I is among the best solution of a given set in an iteration of the algorithm. The second delta is one or zero. Is one if the given vertex is in the best solution since the last restart of the algorithm. That is, since the last time we put all the pheromones on the baseline. And the third one relates the presence of a given vertex on the best solution so far. It doesn't matter how many restarts of the algorithm we have. Is it in or is not? If it's in, it's one. If not, it's zero. At the same time, we update the negative pheromones by a pretty closely method, but we have this chi here, which is one if a given vertex is not in the best solution, that is in the exact solution found among the subset of model of solution components that we have found for any given iteration. And that's a way to discard not so fancy solution components in order to go building a better understanding of the problem. And why do we when we do decide to stop the algorithm or to restart the pheromone values, and that is the convergence factor, which is the same as used in any ant colony optimization in this framework used. So let's move on to the experimental evaluation. We have tested different algorithms. First, an exact solving by Cplex. Then we have the ant colony optimization classical framework by Marco Dorigo and Christian Blum, which is a max-min and hypercube. Then we have our proposed algorithm, which is the ACO plus negative, proposed by Teddy Nurcahyadi in 2021. We have another version, but this of less interest, as we'll see later, and it takes in consideration the negative pheromones. Then we have an ILP memetic algorithm and hybrid tribe intelligence algorithm proposed by the same first author but different collaborators in 2018 and 2020. The hardware we've used is a cluster of machines with Intel Xeon CPU, and well, the hardware doesn't have much interested. And the instances, we used 17 small and medium-sized networks, which are the standard benchmarking networks for this problem, and another 10 of larger value in which our algorithm performs better than any other we've found to this date. The tuning of the parameters, which have appeared in different moments of this talk, has been done with the software IRAs, taking in consideration three subsets. All of this is described in the paper. Finally, the conditions is that the other two algorithms that are an ACO when applied in their respective papers to the 17 instances, and these have to be taken in account. And as an observation, for a concrete instance, we have found discrepancies. So the results, out of all the heuristics, our proposed algorithm is the best on 10 runs and has the average solution also the best, except on one which is problematic for because we think the other papers use a different kind of instance. And for large problems, we see that simplex fails too often, and in this case, our algorithm is the best. So here we have a graph in which we'll appreciate for small instances. We have that simplex performs better than anyone, is an exact method, but followed precisely, but our algorithm ACO negative plus. And in large networks, they are very close. And in some cases, simplex performs better, but in some cases, simplex can solve, and our gives a good enough solution. To end, the conclusion is that ACO negative is the new state-of-the-art method heuristic for solving MPIT's problem, and negative learning proves useful in solving certain problems. Thank you for your attention, and I hope to see you on the live presentation.